Hello everyone, and we're back with a very interesting video today, and it's about data structure. It's about actually an extension to the Disjoint-Set-Union data structure. I call it like an evaluation Disjoint-Set-Union. So this is based actually on a data structure called the eval link update tree. The eval link update tree allows far more, allows this update thing here to happen. And there is a really nice explanation video from don't get me wrong, I don't quite remember, but there's nice explanation video on YouTube. So I wanted to implement just this here because on my faculty there is from one subject of algorithms there is a task which we got, and the task needs us to do this eval and link. I will explain what that means. But this video, I'm recording it quite late on the 11th of March, but this video won't be up until probably 18th of March or 19th of March because the task is actually, like, I cannot upload the video while the task is ongoing. After the task is closed, then I will upload and maybe tell my colleagues about this kind of interesting trick here. The eval link update tree is just the overkill data structure. We don't need the update, but we want the evaluation and link. What does that mean? Okay, so we have like a, so we all know what the Disjoint-Set-Union does. If you don't know what the Disjoint-Set-Union does, you can check out probably you can check out some CP algorithms tutorial on the Disjoint-Set-Union. But this Disjoint-Set-Union is a much more powerful data structure when it's combined with other ideas. So there exists these ideas like Disjoint-Set-Union with rollbacks. There exists these ideas of Disjoint-Set-Union for jumping. So like on lists, it exists ideas about Disjoint-Union with like cycle keeping. All of these I have implemented, but there is this idea with DSU with an evaluation function, and I will explain what that actually is. So we want we want a couple of queries. We want the Disjoint-Set-Union queries such as merge, but this merge query will take U and V as inputs. So U and V will be the parameters of the query, but there will be a strict order between these two nodes. And the U will actually be the parent node. We will attach V to the U, but the U will be a parent of V. So this is important. And V here will be a leader of some set. So it has to be a leader. If that's not true, then you will have to implement the merge function such that V is the leader of a set. But actually this is quite common in DSUs, so that like you find first the leader node here, and then you merge the leader. But this node is very important. So this node does not need to be a leader, not necessarily needs to be a leader. And this merge function should be capable, it should be done in log n at least. And there is another function which is important. We will skip the find set function, rsame function. Rsame is like rsame u and v. We'll skip this, but there is one function we're interested in, and this is an evaluation function. It gets a u, or it gets some node u, and so you can imagine in the DSU, if we have some tree like this. So we can imagine in the DSU, if we get like this node u here, we want to evaluate some function on the path of u to the leader of u. This is leader of u, or the parent of u, or whatever. So we want this evaluation function is actually like evaluate some function from u to the leader of u. Okay, and this function actually will decompose into multiple functions. So we'll decompose from like u to x function, u to x to v, let's say. It will decompose into multiple of these functions for each edge. So each edge has some value. It's defined here from u to v or whatever. And what is very important for this function to work is that this function has to be an associative function. So this means that a function b function c should be equal as a function b and then function c. This is very important. So it has to be an associative function. Yes, and what else has to be? Yeah, and this is a binary function. So there's binary function. So yeah. Okay. So we need to do all of these in log n time. So both the evaluation and the merge should be done in log n time. So okay, so let's consider how I've done this, and look at the I already stress tested the data structure, so I don't have to like I actually started coding it on video. But it took me quite a bit to get all things done. So because first time coding it, and I wanted to stress test it just in case. So I will just explain each line of the code, what it does, and then I will I will probably say maybe a few more things. Okay, so here we create the evaluation DSU structure, which will accept n as the number of different nodes, sets, and then accepts a function for which you get two vertices u and v. U, I think here is like the parent, the leader, and I just do u minus v modulo 1000 because this was in the actual task. So the actual task was to evaluate this. Actually, for each edge you had this value. So if there existed an edge from u to v, the edge here had this function uv, which was equal to the absolute value of u minus v modulo 1000. This could be anything here. If we have u and v, we could use some other data structures to query upon u and v and other things like that, but that doesn't really matter here. Here just we plug that in, and then while we have the file, while we can read the file, there were two types of queries. One query was the evaluation query on u, and the other query was just the merge query, where v is the leader, and then u, I just find the node, the leader of u, and then and then I merge them both here. So I could actually potentially do this here inside the merge function, but whatever. So I just say that, okay, if they are the same, if the set UV are the same, I just don't merge them. Otherwise, there exists now a special thing here. Okay, so let's first take a look at what is this structure. So this is the data structure I explained. It's inspired by the eval link tree. It has the parent. So for each node, I generate this. This is generating such that the parent of I is equal to I. So this is 0, 1, 2, 3, 4, 5, 4, 5, 6, like that. So 1, 0 is the parent. On the 0th element, the parent is 0, and yeah. On the first element, the parent is 1, so it's like just a loop itself, you know, just as a normal DSU would work. So this generates the parents. Then we construct, of course, we resize the parents. We resize lazy with zeros. We generate the parents, and then we remember this function as our operation, what we do with U and V. And this has to be a static function as far as I know. As far as I know, this has to be a static. Yeah, this has to be a static function. I don't think, yeah, like updating the function will just change everything. Maybe you could argue that there are ways around that, but for now we'll just keep as this as a static function. The find set, when you find a set of a node, what it means is that exactly in the DSU what we have. So if we have some nodes here, let's say like this, this node, let's say this node, we want to go up as long as we possibly can until we find the leader node. This is the leader node of this set. And while we do that, while we are going up, we are going to calculate all of these values here. And we are going to update this node's lazy value. Every node has this lazy value here, which will represent what is the value to its leader, what is the how do I say this? What is the evaluation of U? So the evaluation of U will be the lazy value of U. But it's important here to know that the path compression allows us to get this log n complexity, and I won't get to proving that why that's true, but if you wonder, there are tutorials on YouTube how to prove that is true. But the we're not using here, we cannot use union by rank or union by size, because of the specificity of this merge function, that this U here means that it's on top of V. So this is very important. This is, you cannot just swap them around like we do in union by size, right? So when we find the set of U, we actually traverse up. So if the parent view is not U, which means it's not the leader, if it's the leader, I just return this. But if it's not the leader, it means that we're gonna find the leader of U. But while we do that, we want to get from the initial parent of U its value, its lazy value. So this guy here has some value, and this value is actually equal to this function here. Let's just draw an example for you guys to see what actually happens here. So let's say that we have some nodes here. Doesn't matter, it's like that. Let's say here like 7. Okay, so let's say our function of u and v, so of two nodes u and v, is the absolute value between them. It doesn't need to be modulo 1000 or something like that, but just absolute value. Okay, so this function here between 1 and 3 of course will be 2, the absolute value. This will be 6 of course. And now here this guy, this 3 will have a lazy value, should have a lazy value of this guy should have a lazy value of 2. Now let's imagine that this guy is not yet merged here. So let's just imagine that this guy is not yet merged. Let's just imagine they're like that, so they're not yet merged. When we merge two nodes, we take the u node as a leader node, so this is a 3, and we take the v node as a leader of a set. So let's say this is 5 here. They're not the same, they're not in the same set, so with that's fine. And what we do here is a very interesting thing. We calculate the function between 3 and 5. We merge them like this, and we calculate the function between 3 and 5, it's 2. And the lazy value of 5 here is going to be 2. And yet I said that the lazy value here is going to be our answer. But you see that this value here is not our answer, because 2 is only this edge. What about this edge? So here, that 2 edge we're missing here, it's not really 2, right? I mean, if we want to evaluate 5, the correct answer is 4. 2 plus 2. So how do we deal with that? We deal that by this find set function. This find set function, when it goes up from the 5 to the 3, this here 5 gets this value as well. So this changes to 4 here. Let's just delete this. Okay. This changes to 4, and then this whole parent, instead of 3 being its parent, we're going to move this whole thing over here. So let's just delete this. We're going to move this whole thing over here and path compress it here. And you see, this value remains the same, 2 being 2. And this value now gets this value plus its value what is being here before, right? It's got 4. And it's all path compressed now. And this is the power, this is the magic. That's why I'm calling this find set of u, even though I don't need this function here actually by evaluation, but I need to propagate this lazy value. I need to propagate it and then return this value. So this is a fairly simple data structure, but an extremely powerful one, because it allows these queries in log of n time. Merge query, we just calculate for now, like this merge here. We don't care about the path there. When we evaluate, then we will care about the path. Okay? And this is this are two the same. Actually, this works as well. The find set works. So it's quite a simple data structure. And it's quite a beautiful one, I would say. And I will try to make more videos on the DSU data structure, just because it's probably my favorite data structure of all time. It's just simple, it's elegant, and yeah, so this is the date structure. Thank you so much for watching, and I see you in the next one.